just look briefly at the introduction, because what we're doing today is the comparison of all our old geometrical stuff with the generalized coordinate that makes the mathematical methods for all of the general relativity that is being done most of the time now. So we'll be using that notation to develop our generalized mechanics. The various Jacobians, velocity acceleration, all that is going to definitely be treated today, along with the basic kinetic energy form using generalized curvilinear coordinates. GCC will be our acronym for that. And the little trickery that Lagrange did to make that work. And then we'll be seeing Lagrange equations in the form that you would see them in virtually every textbook there is when we get done with this. But we'll have the power to go on and write those equations as they really should be written if you're going to be doing anything with relativity, special or general. So that's the goal, to satisfy Lagrange's idea of equations and bring it, that's the French, and then bring the French together with the Germans, that is the Riemann, Gauss school of analysis, basically, and do that. And then the other screen is sort of the opposite. These are the contras. These are going to be the covariant metric procedures. And that's what the Hamiltonian, that's the Irish school, but Irish brought to live with Gauss and Riemann, okay? So we're doing a heck of a lot of history of mathematics when we cover this, and it shouldn't be left out of the discussion. And if we have a little bit of time today, we'll go into this, through this as well. This is lecture 10. But most of the applications and things that have nice demos will wait for the next lecture that comes after this. So we're really on lecture 9 right now. Okay, now what we need is just to review the stuff we did last time. The zeroth and first equations of Lagrange and Hamilton are taken care of already, and that's what we did in the last Tuesday. And basic idea of having a partial derivative of L with respect to velocity, either in indicial notation or in the Gibbs vector notation. That's the form it has. There's sort of the other equation, that is the Hamilton's first equation, that mirrors this one, is dual to it, is the partial derivative of h with respect to its independent variable momentum. And that gives us velocity, whereas here it's the independent variable is velocity for Lagrangian, and it gives us momentum. So there's that symmetry, you see, between these two, duality symmetry, you might call it. So we're going to be seeing more of that as we go into the second equations of these two people. And the geometry of that is the gradients that have their dual orthogonality. And the duality of orthogonality that is here will be made very clearly evident when you go to the generalized curvilinear coordinates, because that's their whole point, is to make vectors that are dual orthogonal to each other, the covariants and the contravariants, you see. So this is sort of old-fashioned duality. That's the more modern, say, 20th century duality, or really the end of the 19th century. Okay, so we'll be doing that. Now, to do this, we're going to take the simplest curve coordinates I know of. Cartesian's too simple for us to do. But having polar coordinates as our first try really is helpful. And we're going to just carry it all the way through. It's two-dimensional, so you don't have to write much. It's well-known form that you've seen, sine, cosine. And the equation here where I give the curvilinear coordinates in terms of x and y are the more messy of the equations. What we're really interested in are the equations that simply say that x is r cosine of theta and y is r sine of theta. Okay? So that is a key thing here. And what we need to do is rewrite our differentials in terms of the curvilinear coordinates, the polar coordinates. So we're going to be interested in differentials like that and looking at them fairly carefully. Now let's make sure that we're, inverting this equation is this, but I would prefer to, I think most people would prefer to start with this, and then maybe if you have to, work with the inverse relationship between Cartesian and polar. And you can see that's going to be the rub when you work with curvilinear coordinates. It's not guaranteed that you're going to have anything that's even easy, certainly easy to solve, where you give the curvilinear coordinates in terms of the Cartesian. But it's more common to have a simple relationship for the Cartesian in terms of the curvilinear. You see. But in any case, whatever, we're interested in differentials. And the inversion of the differentials is simply a matrix inversion. So that's always going to be the same amount of mathematical labor, regardless of what the curvilinears are that you're interested in. So the first relationship that we write down is a relationship that involves the Cartesian differentials, a matrix called the Jacobian, and the spherical coordinate differentials, dr and d theta. And from this equation right here, that works out to be this matrix here. It's almost a rotation matrix. If r is equal to 1, it really is, right? So that's nice to point out. Now, here's what it's going to be in general. The GCC, generalized, or I might call Gauss curvilinear, because he's really, I think, before Riemann working out stuff like this, are almost all of the literature indicated by the letter Q. Now, why? Why did pick Q out? The best I can think is Q for queer. We're going to have some pretty queer coordinate systems before we're done here. And one of my main tasks is to make them not so queer, to make them look quite natural. And that's what we'll do with a complex variable review. You just name a function in complex variables and you get a set of curvilinear coordinates that you can play with, you can really understand. In any case, we will use Q for a lot of the stuff that we do. And of course, we'll use the old X, Y, and Z, or X1, X2, X3. X4, if we're going to play relativity, okay, we'll be using very standard notation there as well. So this is the deal. And also the thing that's not going to be present in any of the equations we have, except implicitly. It's called the implicit dummy index rule. And the basic idea is if on one side of the equation you find an index repeated, then you sum over it on that side of the equation. It shouldn't be on the other side. If it's on the other side, don't try it, right? But if it is just on this one side, then you do a sum, okay? And that eliminates having to write sigmas with stuff over it. But I would warn you that if you're actually going to be doing calculations, it does help to draw a line between the two, or maybe more, that are repeated. So I would normally do something that you just can't do typographically in a text very easily, by making a figure out of every equation. And that's just draw a line between the two. And if you need to be reminded how many times you have to sum, you might put that, this number here in there. But you probably don't have to be reminded that you know what your dimension is usually. Okay, but this is, when you have a long complicated equation, really helpful to put lines between the things that are being summed. Okay, now, this is what I say right here. As I say, the connection lines may help. Okay on scratch paper, right? You'll not see this in the text. I can do it in the keynote, but in actual text, it's pretty hard to do. I don't even know if tech has the ability to do that. Probably the Russian tech, the guys figured out how to do that. But anyway, okay, so we're going to do two lemmas here. These are the key things that you need to take on generalized curvilinear coordinates as equations of motion. So the generalized velocity comes immediately from our differential, our first order differential of the curvilinear summed over however many dimensions we have. And the velocity component, here Cartesian, 1, 2, 3, x, y, z, okay, or x dot, y dot, and z dot, okay, is derivative of x, y, or z with respect to time. And that means then that we can indicate here a generalized curvilinear velocity, okay, or generalized curvilinear coordinate velocity in the same way that we do for our Cartesian coordinates. So that is not anything terribly new. And in fact, if you write it this way, that's your first derivative expression right there for velocities of the ordinary Cartesian and then the queer coordinates, queer GCC coordinates there. So that's just a first differential relationship, and it will involve a Jacobian matrix, that is this matrix for the velocity as well as the coordinates. So that's the first lemma. It's almost too obvious to write down, but I'm going to do it anyway because the second one is kind of like this one, just a little more sketchy. Okay, so that's kind of neat that I don't need a velocity Jacobian because it is equal to the coordinate Jacobian. That's what we're getting out of this. Okay, so let's just mention what the Jacobian is. We already showed a picture of it as being like a rotation matrix, except it has R's in front of this second column. It doesn't have an R in front of the first column. That goes away as partial derivative with respect to R, which is what the first column is. So we'll give it sometimes a letter J for Jacobian, and Jacobi will enter into our discussions in the next few lectures in a big way. Here it's just bookkeeping, but he's got some real physics for you later on, he and Hamilton together. But this little guy here, which is equal to this guy by the first thing, that's the matrix, in this case 2 by 2, that we're working with. Now, this is my jokey, and I think other people have done it too. The so-called Kajobian is simply the inverse of the Jacobian. And the idea is that all you need to get the Kajobian is a matrix inverse. Well, for a large matrix, that's not trivial. For a 2 by 2, it's something you should always have in your head. Basically, all you do is you switch the diagonal elements and then you put a minus sign on the off-diagonal elements. Then you divide by the determinant. That will make you an inverse. So this is what the Kajobian looks like for this particular polar coordinate GCC. Okay? And if you write the whole thing out, that's really what we're looking at for matrix inverse. But I warn you, just if you're using this on some kind of exam, you really want to test your inverse every time you make it, no matter how you make it. So that's what we're doing here. Just make sure that when you multiply these two together, that you do get the unit matrix. Or if you're just multiplying it without that extra determinant of Jacobian factor there, that you get the Jacobian determinant when you multiply these two together in the diagonal, right? So there's the test you would actually be doing most of the time to make sure you're right about your thing. Because if you ruin that, if you don't have the Kajobian right, everything you do from there on is complete crap, right? So you really want to make a test before you do too much more writing. Okay, so product here is written out in the notation that uses this tensor notation. That is, I'm summing over J here, summing over J here. It's just a rewrite. And I'm getting the partial derivative of Qm with respect to Qn. Well, by the definition of partial derivatives, that should be 0 if they're independent variables that are different. If it's the same variable, then a variable with respect to itself is 1. So this is the key thing that's going to be making it possible for us to have this dual orthogonality of our coordinates eventually. Right now it doesn't look like much. It's true for every possible coordinate that has a derivative. And it's basically connected with the fact that the product of these two is a unit matrix. Okay, now let's get to something where it really makes a difference, that we are dealing with curvilinear coordinates. The reason that we could have such a simple lemma for velocity is that, well, for velocity we need the first derivative. But here we need more than that. We need the first, and then we need a derivative of that derivative. So what you're looking at here is acceleration, and you need to use the product rule. Because if this expansion, this chain rule expansion for x dot j, and that's the partial of xj with respect to each of the queer coordinates, summed over the queer velocity, right? That's dqm dt, okay? Each of those has to be differentiated in turn. Derivative with respect to time of a product is product of independent derivatives. So we have to go through, we have to take a time derivative of the Jacobian in general, multiply that by the velocity, okay? And then we get a thing here that's just the Jacobian times an acceleration, okay? Now, if it turns out that this thing here is time independent, if you really do have a time independent Jacobian, that means you don't have anything in there that's changing. That means you don't have any coordinate dependence. If this is a constant matrix, this is gone, you see, and we don't need to worry about anything but this. We can do the same thing we did with velocity. Instead of having q dot here, we have q dot dot. And anyway, when you apply the derivative in this way, you get a second order partial derivative. Okay, so this partial with respect to qn is then happening after I've already done a Jacobian, which is a partial with respect to qn. But remember, they're reversible. This is this thing that came with lecture 9 as a review of calculus. If they are reversible, then I can turn them around. And once I've done that, then I can say this is a partial with respect to qm of this. Jacobian times the velocity, qn dot. Okay? And that thing right there is just x dot. That's Cartesian coordinate velocity. Okay, so that's really what we're dealing with here. And that leads us to this lemma 2. We're going to need this along with a lemma 1. And they're kind of the same thing. They're about what do you do with derivatives of things that have dots on them already, or are about to have with here. So this is kind of interesting. I take a time derivative of this, and I don't have to worry about the time derivative of this. I only have to work with the time derivative of the Cartesian. So it's these two. This one just says, put 2 dots on the Jacobian and it's okay. That one's a little more subtle. Okay. All right. So now we're going to do what is essentially all of the classical mechanics that most people get. And that is how to say Newton's F equal ma in GCC. That's pretty much it. Then you just go and do all kinds of weird machines. That will come later. That's what the unit I just gave you is where we tackle the Trebuchet, which is an awesome machine that reproduces human motion a little bit. So we're going to first of all have a look again at what you would expect the kinetic energy to be and what F equal ma would look like using queer coordinates, Q's, and we're going to see Lagrange has some nice little trickery, just a few little tricks here that if I were to ask you to just go off and you were going to flunk out of graduate school unless you derive Lagrange's equations from this point, that you might spend a bit of time discovering these little tricks. Okay. First, the first one is really quite an interesting thing. It should be remembered for other things. That's one reason why I'm going to illuminate it so much. Okay, now here's the deal. Remember when we started talking about making velocity tensors, second forms like that? Okay, things like this. Our second forms were all diagonal. There were superball masses along the diagonal of the matrix, right? Well, now we're going to allow there to be off diagonal. And you will immediately get things like that if you're doing any kind of rotation of something that has a non-trivial inertia tensor. Right now the mass tensor for the superballs was always diagonal, but if you change coordinates and use combinations of coordinates for the superball, then you would have off-diagonal terms there. So that's kind of a justification that I should be doing this. I should be allowing for this extra structure. And if I'm going to have an extra structure in the kinetic energy, I would have the same extra structure in F equal ma. So I would have a force due to some acceleration, okay, would involve perhaps n terms if it's in n dimensions, not be an eigenvalue equation. Okay, so that's a possibility that we really need to take into account. And we surely need to take into account if we're going to do classical mechanics of circuits, electric circuits, which is very interesting stuff. And almost always the inductance has mutual as well as transfer inductances. So there's a case where you definitely have an inertia that is off-diagonal matrix. Okay. So this is really the start, F equal ma, but now with these bizarre off-diagonal, completely full matrix for the inertia. So what we're going to do here is go ahead and rewrite the F here, that is dxj, that multiplies the force to make what we mentioned before is work, force times distance. But now we're going to rewrite the differential in terms of the q's. And we're going to do it for both sides. In other words, we're pretty sure about this, even though we've made this new kind of inertia. Now we're pretty sure about this, but it's a big old sum, so what are you going to do? Now we've got it written in terms per coordinates, so how are you going to get an equation of motion, a thing like that? That's not trivial. Until this thing really breaks the ice right here. These are supposed to be independent, supposed to be true no matter what differentials you take. So it has to be, since they're independent, it has to be true term by term. It still holds if all the dqm's are 0 except for 1. If that were the case, then you would not have a sum over m. You would just have one term involving a single m. So the idea is that this sum here, because they're independent differentials, is equivalent to this one that just involves one particular, and any one particular GCC coordinate, the mth GCC coordinate. So that's a big icebreaker right there. Okay? We've now got an equation that's going to be well, it's still written in terms of x's, but I want to get it entirely in terms of q's. You see, that's the goal here. So this is the what we're going to call the generalized GCC force. One of those terms, either written this way or written this way. So this is the F equal ma part of the equation of motion, but it isn't going to come out that way. It's going to come out in a Lagrangian form, which we have to get with. So now begins the trickery. And this first trick here, as I call it, clever end game, is to treat the m x dot dot as factor A, and then b as the partial derivative, a Jacobian basically. So b is a Jacobian component, okay? And one of these, this A here, this guy right here we're going to be treating as A dot dot. So this is a double derivative, you see the dot there. And at this point, one of the things that you're going to be demanded, and this sounds like almost too much to demand because we're going off into queer coordinate land, shouldn't this thing also be a function of queer coordinates? And the answer is no, no, no. This has to be constant. It's Cartesian. Okay, that has to be a constant. Okay, so it's only differentiation with respect to time is going to be for that variable right there. Okay, and then it's just ordinary calculus. We're going to rewrite A dot dot B as d dt of A dot B minus A dot B dot. Okay, so this is what it opens up to. So this is the big trick that makes a Lagrange equation, right there. Well, we have to sort out here, you see. Okay? Does that make sense so far? Go to the next step. Okay? This is where I say, it isn't going to work unless those are constant for this to work. So, I say, if you're starting with a curvilinear coordinates x1, x2, x3, goodbye. Okay? Relativistic mechanics looks like it's going to be out of business unless we do something else. And we'll do that something else later on. But right now, we can't have that thing changing. We can't have masses changing velocity. Okay? This has to be good old-fashioned Cartesian. Okay, in order for this to work. Okay? Now, I'm going to use lemma 1 and lemma 2 to make this more complicated. I'm going to go to the complicated side of the thing. I'm basically replacing partial x with respect to qm with x dot with respect to q dot. Okay? Going in a direction that I wouldn't normally go. This is more complicated than that. Why would I want to take something that's pretty simple and make it more complicated? But the answer is obvious and just another line here. And the same thing with this one right here. A derivative with respect to time of this Jacobian, that's pretty simple. I want the partial derivative of the velocity with respect to q. That's lemma 2. Okay? It's starting to take form here. Because you see I have an x dot here and I have an x dot there, I have an x dot here and I have an x dot there. I can put that together as a single derivative, right? And that's what happens next. You take this form and make it into that. Kind of like what we did when we mentioned the kinetic energy was a v squared over 2. But this is a little more sophisticated. We're talking about all these components, right? Okay? So you end up with this. There's kinetic energy. There's a partial respect to Q. We're done. Except you might want to rewrite it a little bit in the notation that's used. Okay? So this is what I call Lagrange's GCC force equation. Because it's still got a force in it. We're eventually going to get rid of that for very special forces that are conservative. But this is what I call the, I guess, the tensor analysis four-wheel drive garbage truck. This thing goes anywhere. You take any problem with curvilinear coordinates, and you can use this. It can be moving. It can be all kinds of things. It can be a real mess. The idea is it's a four-wheel drive garbage truck. You can take a load of shit and go anywhere. Okay? So this is an equation that's sort of the bedrock for just doing machinery that has complicated parts. And even friction can be present if you're careful and you make a few adjustments. Anyway, that's the basic idea. And here's sort of the Gibbs notation way of writing this thing. The time derivative of the partial of the kinetic with respect to all, whatever velocity and whatever position. Okay, so that is certainly a way we could have written Newton's laws as well in Cartesian coordinates. But this is the one that we will be actually using most of the time to start with. Okay, but there's this second way of doing this. If the force is conservative, so that it's a gradient, that is a partial with respect to boldface r, or Fm is minus the partial with respect to queer coordinate q, curvilinear m, then I can take this guy right here and sort of stick him next to that guy right there. That is, add him or subtract him. In this case, I would add him to this, and it would be minus t minus u. Okay? And then, what are we going to do with this to make it look like that? Well, we have to demand something. We have to demand, in this trick, this is the second trick, we have to demand that this u here, this thing that is the potential, has no, absolutely no, explicit velocity dependence. In other words, the partial of it with respect to velocity has to be 0 if I want to stick a thing like this into here with a q dot. Okay? Then I get an equation that looks like this. And that is a very standard form. You'll see it on the wall over yonder, right there. Okay? Where the Lagrangian is the difference between the kinetic part and the potential part. And the potential part better not have any dependence on velocity. Now, in order to do electromagnetism, we're going to have to fix this. Because electromagnetism has lots of things that, if there's a magnetic field around that depend on velocity and you get some charge, we're going to have to fix this. But that will come later. We got enough things to worry about right now. Okay. But this is certainly an elegant. Now, is this the most elegant way to write it? Absolutely not. This is the way you can remember it. Remember our first GCC equation? That momentum is defined as the partial of L with respect to the velocity? Well, that's what we've got here. Okay? Here's the second equation. It's that the time derivative, total time derivative of the momentum is equal to the first derivative with respect to the coordinate that you're worried about. So the two forms of equation are found by taking a dot and putting it there for the first one and putting it there for the second one. That goes into weak memories like mine very easily. This one Not so easy. Okay? So that's kind of cool. The first and second Lagrange equations just amount to moving a dot between the P and the Q. Okay? And the P is always outside, and the Q is always in the denominator. Okay. Good enough. Now, something that's implicit to this that's coming later, and that is, why do I draw the indices for P down, whereas the coordinates, and that's just, apparently Gauss did that and that was it, but the coordinates have their indices up. Now, when the indices are up, it's called a contravariant quantity. How do you remember that? Well, I think of the iron contras, okay, with their daggers up in the air, okay? So when your dagger's up in the air, you're contra, okay? But the covariant things are downstairs. So that's really what we need at this point to discuss, and this is what's so rarely discussed in classical mechanics, the generalized curvilinear coordinate duality of contra and co-variation, variance. So that is what's next. But before we go there, any questions about what we've got so far? Because we could just write all of the indices down like most books do, and we'd be off to that kind of races.
Why do they call them contra and covariant?
Why do they call it contra?
And covariant.
And co?
Right. Because
I think it's due to Riemann.
Right. In more modern textbooks, not classical mechanics, mostly differential geometry type textbooks, you don't find that language anymore. They just call it up or down indices.
And that's a mistake, because you really need to respect the duality. And what co and contra correspond to in quantum mechanics is bras and kets.
Right.
And usually the kets are the contras, and the bras, which you don't use that much, are the cos, but that doesn't work here. We use them both equally here.
Right.
And so we'll discuss that later. That is something that your question has bugged me too.
Yeah, I think really the idea was nobody could remember which one down, you know, as compared to up.
But then the iron contras came along, and Reagan's, right? Remember, that should have put Reagan in jail, right? I mean, that whole business where he's giving him weapons that he stole from somebody else, I mean, that whole thing was a big slimy trick, right? So, let's use it for our mnemonic purposes. Okay, we get something out of that disaster. So, we'll use polar coordinates, which don't really need to go co and cont because they are already orthogonal. But it helps even them to know which one you're dealing with. And basically it comes down to quantities that are extensive, like space, size, and quantities that are intensive, like momentum or current or something, you know, something that has a density associated with it as opposed to a size. So it's a case of looking at a quantity or its inverse very often. And they are sort of the inverses of each other, as we are going to be seeing here. So here's what happens, and it's really kind of neat. And that is that the Jacobian columns are the covariant vectors. So as soon as you write your Jacobian down, the first thing you should do is say, this vector here is my covariant R vector, and this vector here is my covariant phi vector for the curvilinear coordinates of R and phi for the polar coordinates. Regardless of what, this could be electric field, a component R and phi, for example. But it's not. E stands for elementary vector, I think. Okay, so that's what you do. And then you take the inverse of the Jacobian, which is the Kajobian, and now the rows of the Kajobian are the contravariant vectors. E super 1 and E super 2, or E super R and E super phi for the polar coordinate case. Okay? So you can look and see how those vectors vary. I've drawn these in blue on here, and you can see that as I go out, the R never changes. It is really quite dull in a sense. It just makes an R cosine sine vector that's unit size. Okay, all of the things are the same unit size. But this one's trying to track the size of the cell that it's attached to. And so it goes up, up, up linearly, just like that. So E phi, the E sub 2, goes up, 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 up as you go out. Okay? It's tracking the cell. We'll get to that in a minute. That's the idea of symmetry. This thing right here is trying, it's not doing a very good job of it, but it's trying to set out the real estate marks for this piece of property here. It's kind of missing because it's curved away from it, right? But if you made this a real fine graph, right? So that you're down here looking at the picture like, then it'd be right on. Just a little bit off. Okay? So that's really an important thing that's true of the covariant guys. Meanwhile, these guys do just the opposite. As they come in, they get bigger and bigger and bigger. Okay? Kind of like a whirlpool, and we're going to be seeing the mechanics of a whirlpool after we get done with this. Okay? So that shows up very, very clearly here with that 1 over r. This doesn't have it. It just stays good old unit vector. Okay? That's these guys right here, you see. Okay. So that thing. So here's a general sort of picture of what you're going to see. When you say dr equal partial derivative of q1, I'm sorry, of r with respect to q1, that's what you call E1, and then E2 is partial of big fat R with respect to Q2, right? You're talking about a first order differential. And if dq1, if they're actually 1, let's just put a 1 there, right, then this would be the sum of E1 and E2, namely that vector. Well, it won't quite be right because even though I'm talking about a unit 1, which is pretty small compared to the units we're actually using here, 200, 201, 100, 101, right? Those are the Q constant level curves that make the coordinate grid, okay? And I point out that these drawings are 2D drawings. This is all in a plane. Your eye says, hey, that looks like something that's curling out of the screen, right? It's not. These are not 3D perspective drawings. Okay, and this one even weirder, but it's the one that's based on gradients. The gradient of Q1 is this. This is just the partial derivative of R with respect to Q1. This is the partial derivative of the Q1 with respect to R, the Cartesian R, right? That's a gradient. So as the gradients get bigger, these will get bigger. They are interested in the gradient of the thing. But what they're also interested in is being perpendicular. E2 is perpendicular, this 90-degree angle here, with the level curve Q2 equal 200. And then the other one, Q1 equal 100, sends the E1 off like that. So I'm going to have several exercises for you to put the right numbers and right vectors in some queer grid system, just to get used to so you really can think about what these are. In any case, what I'm trying to do is really distinguish these two. In other words, you mentioned before they kind of don't know which one is cold and which one is cold. Yes, we do. It's like inside and outside. And this is the giveaway right here. That's definitely cold. The one with the gradient is definitely contra. It's always perpendicular to everything. It won't go along with the coordinate lines. It goes perpendicular to them. Okay, contra. Okay, so as I say, they match the unit cells. Okay, so that's something that really makes sense here. The E1 follows the tangent, right? As Q1 varies, right, that's where it's going to go, okay? And that means this thing varies, this thing goes along making Q1 bigger, but it always tries to stick to Q2 equal constant, because that's what the partial derivative means. Is it means you take the derivative of this with respect to Q1, but you must hold Q2 constant. That's implicit. And then this is the opposite case. Okay? So that's a key thing about the covariance. And this, we'll just jump ahead here, this way of writing a vector, and velocities and momentum kind of often can be written this way. It depends on what you call. I really think that I would use this sort of notation for spatial things sometimes, not others. But in any case, when I do use this a covariant-like thing, fine. As I say, extensive quantities like distance and velocity deserve that. Okay. These guys here match are more for intensive quantities. So like force or current or something like that. I think that is a better physics by using the covariant components, contravariant vectors. This one's just the opposite. Okay, so I point here, it's normal, it's gradient, and so it's a vector sum of the partial derivatives that make up the Jacobian, but here it's got the Kajobian components being used. Okay, as I say, intensive quantities like force and momentum. That makes sense there. Okay, now here's something that definitely happens, and that is the dot products of cos with cons are mutually orthonormal. And why is that? Well, here's the co, it's partial with respect to a contra, but the contra is in the basement. Whenever a contra is put in the basement, he's much more cooperative, right? He's locked up, right? Okay, so he becomes covariant. Okay, whereas this guy right here, he's upstairs where he can do damage. That's this vector right here with the contra up in the air. Okay, well, summing over R, that just makes a partial derivative of Qn with respect to Qn, which we already mentioned is a delta. It's 1 when you have the same coordinates. It's 0 because they're independent when you don't. So that's the rub right there, is that this vector here, E1, has got to be perpendicular to E sub 2. It's perpendicular to it, right? Because E sub 2 goes along. It goes perpendicular. See the same thing here. These two are orthogonal. Okay? There's your bracket business right there. The red things, I guess you could call these jets and those bras, or vice versa. There we don't really know because hardly anybody assigns much use to the bras. They should. There's a whole thing that you could do with that is very helpful.
This would only be true in a flat space, right?
Well, if you're back to Cartesian coordinates, even weird ones that have more scale this way than that way, you're right. You would already have orthogonality of the vectors there. But this one just happens to be, the polar coordinates that we're using just happens to be not just a GCC, it's an OCC, orthogonal curvilinear coordinates. Okay? And I find that most books on mathematical methods will take you up through orthogonal curvilinear coordinates and then just throw you off the cliff. There's nothing on how to deal with the ones that really matter. In GR, certainly, but also in hydrodynamics and optics. Okay, so let's just go through this because basically what's going to come down to is we're going to have Lagrangian, Hamiltonian, and a Strangian. philosophy, right? This one giving us what we're going to be calling the covariant metric coefficient or metric tensor. And this one, the contravariant metric tensor. It's got two knives up in the air. It's really contrary. And then this one has up and down. And it's just circular. It's really simple. If you can get stuff in terms of it, go for it. And in principle, you can, even when you're dealing with the nastiest curvilinear coordinate system, away from singularities, of course. So that's a key thing to note here. Again, here's the polar coordinate example with the contours in the columns, the contours in the rows, and that's sort of bra-like, and then these are ket-like, they're column vectors. Those are the covariants. So the column CO goes with covariant CO. Okay. Cooperative, I guess, would be the thing to think of. And then the contours are the other one. Okay. So in quantum mechanics, you usually don't work with the bras, but why not? You could. And in group theory, there's a really good reason to do that. Okay. Here's what the metric looks like. If I go and do ER.ER, I just get 1. It's a unit vector. I get 0 for those two, because this is an OCC. Okay? And then I get R squared for that one. Okay? Meanwhile, over for this one, I get 1 over R squared. So this matrix is the inverse of this matrix. Then this matrix here has to be the inverse of this one. This one's the inverse of itself. So that kind of sums up what we're going to be dealing with as we play with these generalized curvilinear coordinates. And they can take anything. They're perfectly happy to make a coordinate system out of that fountain of parabolas that we made. Those are coordinates. They're all kind of, you know, going along with each other, right, and making very skinny parallelograms. Perfectly good coordinate system as far as the GCC is concerned. So there are all sorts of cases where you can take really complicated optical meshes and make some sense out of them. And make them the coordinate system of the system that's being studied. That's really what this relativity stuff is all about, and making the system give me the coordinates. What do you want to use, Mr. System? I start making my own coordinates and I get all messed up. I don't know what the hell I'm doing. The system knows. Let it tell you.
Perhaps those that follow the constraints.
And that's right. When one coordinate is being held constant, well, that's a big deal and easily computed. Okay. Now, it turns out Lagrange, if he had used this German method, would be preferring the covariant metric when he made his energy, and he would use velocities, and the velocities will be contravariant. Whereas over in lecture 10 there, it's rather the opposite. As I point out, we've left it up on the screen conveniently here and not kept up with everything. But Hamilton prefers a contravariant metric if he would go with the Germans, okay, the Gauss and the Riemann. He didn't so much, but if he would have, that's what he would have dealt with. And then he would have been talking about momentum because it's covariant. So we really mean it when we put the PM down, the M down. It's a cooperative thing, not a contra. Okay, so we're going to go through this, and on the process we're going to take care of Coriolis effects very elegantly, as well as centrifugal and centripetal. So here is Lagrangian kinetic energy T minus U, and it's supposed to be, this is Lagrangian, it's supposed to be an explicit function of velocity, okay? So we just go without any problem in this. We've got to deal with Hamilton. We've got to make it an explicit function of momentum. In any case, that's what we've got here. You see, here's R dot, I mean R little dot, dotted with another r little dot, okay? And each one of those is a covariant vector summed over the velocities associated, and the velocities are contravariant. So r and phi are being summed over there. And the em dot en goes right away to make your metric tensor. And then there's the q's that are left over from that. So that's really all that's going on there. That's writing a metric relation for the Lagrangian. Okay? Well, this is kind of neat because really what you're doing, if you can divide out some things here, is you're asking what is, using the metric tensor, what is distance? You know, we're talking about a velocity squared. We're talking about kinetic energy here times some constant. The constant is fairly simple here because the mass is going to be the same in both dimensions as it would be for any particle flying through space, ordinary Cartesian space, and we're now writing it in polar coordinates. So when we do this, everything will be the same as Cartesian except this one component in the metric tensor, g phi phi, is going to be r squared. Okay? So this is the way people would have just jumped in and written this for kinetic energy. But you see, it's already telling us something. It's telling us that the inertia that goes with the phi, that is mr squared, that's the rotational inertia. This one here we all know about, that's just mr squared, right? So here's where the geometries come, and if you haven't learned that the rotational energy, inertia is mr squared, the GCC slaps you up the side of the head and says, hey, you do need the r squared. Okay? Well, that's what's going to happen all through our writing of the equations of motion, is that the various things that we have names for, Coriolis, centripetal, and so forth, come automatically. They work up quite automatically. Okay? So this is just the preceding page that we were looking at here, and now I'm going to write the first L equations, first Lagrange equations. And what we're going to be getting, of course, from these is whatever the generalized momentum is. Okay? Now this one isn't very surprising because we only have a 1 here. We take the partial derivative with respect to r dot. And remember, when you're taking a partial derivative with respect to r dot, all the other variables in this thing, coordinates, phi dot, they're all not going to move. This is implicit to keeping them all constant, you see. So I'm not going to get anything from this, I'm not going to get anything from this, because there's no r dots in there. It can't be for this to work. And I'm only going to be seeing this term right here, and so the 2 cancels to 1/2, and I'm off to the races with what we know is momentum, mass times velocity in a radial direction. See? So no surprises here, because this is not a curved coordinate, right? The first curved coordinate is this one, okay? So I go and I get my g phi phi out, that's mr squared, bingo, okay? Now, I can't overemphasize this wow. You see, this is where the mathematics, the geometry, the Riemann genius, all that kind of stuff is helping you. This is angular momentum. Using these queer coordinates, phi dot usually calls omega. You see, so what a help, right? What a terrific benefit you get just at this first equation here, just this one, okay? We still have to do the motion, that's going to be a little harder, but not so much, okay? So here we are, having finished the first equation, we go on to the second Lagrange equation, the total time derivative of momentum, okay? Well, it's supposed to be the partial of L with respect to R, okay? So we are going to have to take a derivative with respect to r of anything that has an r function in it. Not too many things that have that right here. In fact, it's only this one. Okay, so I've got to go and add to that this thing right here. But then the rest of it, partial L with respect to r, will depend on whether u has any r dependence in it, right? And if it does, it should be written down, okay? Whatever that is, all right? Now, look what you're getting out of this one. In addition to the force that would be due to the gradient in the radial direction of this with a minus sign, this is physicist force, right? The other physicist force that's going to make this thing go is this one. This is positive. And what is that called? Center fleeing is positive. Fleeing, fugal force. mr squared omega squared. I'm sorry. mr omega squared, right? Or mv squared over r if you want to replace the omega with v over r, right? Okay? So, big deal. I say wow again. Okay? Now this one, the next ones that are going to be coming out here are more of a wow because Coriolis is really not something you have a very good feeling for until you practice. Okay? But one of the things we're seeing right here for this one, and this is also important, is that if this particular Lagrangian has no phi dependence, and that means no problem with kinetic, I don't see any phis there, but there could be one here. So if I don't have any bumpiness in the potential, if it's isotropic, this is identically zero. Okay? So that says that p dot, the momentum that we just derived up here, with respect to phi, that phi component, okay, constant, or as they like to say, conserved. Okay? Potential has no explicit phi dependence. Forget about any motion of p phi. Whatever gets set at x is going to be that way forever. Okay, so that's cool. Now the whole symmetry associated with that says no, if you don't in your potential find any lumps, then when you go over it, you won't get any bumps. Okay? No lumps, no bumps. That's sort of an Arkansas way to say what that equation is giving you. Okay? And the roads in Arkansas used to be all lumps and all bumps. Now we've got some pretty smooth ones. All right. So that's this. Now there's still something to do here. After you've gotten those two equations of motion, you can do something to make a kind of equation of motion that you put on a computer more directly. And that is you find p dot r and p dot phi, if there were a p dot phi. It's not going to be one, so we're going to mostly concentrate on this one, directly from the first L equation. In other words, directly by explicitly doing the derivative with respect to time of that term associated with this particular m equal r, the r component, the radial component, okay? And then you equate that to the p dot that you got from the second Lagrange equation. So that's the sort of dirty manipulation that you usually have to do when you're using Lagrangian equations. So we'll go ahead and do that, because that will be giving us the canonical force. Okay, so that's what we're about to perform here on these slides right here. So we take this one. That's pretty easy. P dot r is just mr dot dot. Okay, but from this equation right here, okay, what we get for the p dot dot is our little centrifugal thing here, center fleeing thing, and the gradient of r. Okay, so there is your equation of motion. Mr dot dot is equal to centripetal plus the physicist's potential force. Okay, there's a center pulling force if this were positive. Okay, something holding it in, and then there's the thing that wants to take it out. So there's an equation of motion that makes some sense. Now it gets really squirrely because it involves Coriolis forces, okay? When I take the P phi here, okay, if I take that P phi right here, mr squared phi dot, and do a time derivative, and here you have to remember, I mean the total time derivative, not a partial time derivative, okay? A total time derivative of this thing, okay, involves anything that can move in here. Well, mass, we're not letting that move right now, but later on we can have that move. But we're definitely going to have R moving, and we're definitely probably going to have phi dot moving. Okay? So I'm going to get two terms out of that right away. Okay? And they have names. This one is the Coriolis, and this one's angular acceleration. There's your inertia, right? And there's your angular acceleration, alpha is what they usually call that, right? So, I hold this up to you as if I was a salesman from the French school as pretty cool. Okay? It's doing stuff that you really have to scratch your head at if you're just using Newtonian XYZ. Okay? And let's just look at the weather. Okay? This is what we're dealing with here. I'm interested in how that's going to change. How is our equation of motion really going to change? We have a radial acceleration. Okay? We have an angular acceleration. Okay, maybe. Well, it depends on the weather, really. Let's take a case where we're in the northern hemisphere. That's where we are right now. Okay, we're talking about phi dot greater than 0. Okay, so here's the globe, there's the North Pole, right? The sun comes up as you rotate around, right? So that's, I should use my right hand to indicate a rotation of the Earth, you see. And that rotation is down this way, okay? Now, what I'm interested in is a low pressure area, okay, which we're going to be getting come this weekend. Another low pressure area is going to move in, okay, and it's already established this motion, okay, but R dot for a low pressure area is less than 0. R dot is negative in this equation. So phi dot is positive, R dot is negative, and a negative negative gives a positive, so I'm going to end up with this term here, phi dot dot, being positive. That is, as this stuff comes in, it's going to try to rotate, and this is where the quantum mechanics comes in. It's going to try to match the rotation of the Earth, because that's what really costs. The waves that go in the same direction as the thing that holds them have less energy, less beating, less frequency problems. So that's the easy way to remember which way low pressure area turns. It's going to turn to match the turning of the planet it's on. And here we're at some middle latitude, right? But still, that's the kind of rotation we're talking about. Okay? Result. As the low pressure area approaches, it's going to be warmer. It's going to bring warm air from the south. And more moist air, because we've got a Gulf down there full of water, right? And the United States had the worst case of tornadoes, which is what you're going to get. A really big tornado always goes that way. Some small ones can be going the other way, but a really big one always goes that way. Along with a whole weather front that's involved in. Okay? So, as I say, this is, a way to begin to understand. And then after it passes, next Monday, we're going to be seeing pool again. Right? Now you'll see the same thing in other countries. Europe, India, you're above the equator, this applies. If you're down below, it's the opposite. Okay? Well, as I say, deep quantum rule, flow tries to mimic the external rotation. Least relative velocity, that's what really counts. I think it's probably a good idea, since we are pretty much at the stopping point we should be, that we come back. This thing has a review built in, so we'll go quickly through the Lagrangian. So I think we'll just go ahead and stop right there.